All right, let's talk about Google's latest beast in the world of AI. It's a system called Ironwood, and it's their next-generation AI supercomputer. We're going to pull back the curtain and really dig into the architecture that makes this thing tick. But first, to give you a sense of the sheer scale we're dealing with, I've got three numbers for you. Brace yourselves. First up, 9,216. What is that? Well, that's how many of these new Ironwood chips are fused together into a single Google Superpod. And let's be really clear, this isn't just a small step up. We're talking about a profound leap in scale. Next number, 1.77 petabytes. That is a mind-boggling amount of memory. We're talking over 1,700 terabytes of high-bandwidth memory. But here's the secret sauce. It's not divided up. It's one giant unified pool of memory that every single one of those chips can access directly. And for training today's monster AI models, that is an absolute game changer. And finally, the raw power, 42.5 exaflops. You might be asking, what's an exaflop? It's a quintillion. That's a billion calculations every single second. It's a number so big, it almost loses all meaning. So you take those three things together, the chip count, the shared memory, the pure computational force, and what you have is a brand new benchmark for AI infrastructure.
Okay, so you've got this digital giant, but having all that power is one thing. The real engineering magic is how you get thousands of different parts to think like one single unified brain.
I mean, really think about that for a second. How do you get over 9,000 individual processors to share data so fast that they truly act as one? It's like trying to get an entire stadium of people to have the exact same thought at the exact same time. That is the fundamental problem this architecture was built to solve. And the answer is pretty incredible. It's a technology called an optical circuit switch, or OCS. The best way to picture it is like a ridiculously fast, hyper-intelligent telephone operator for data. But instead of copper wires, it uses light to create direct, physical connections between any chips in the system, on the fly. The result is this massive, totally reconfigurable web of light. And that flexibility is its superpower. It means you can literally carve out custom-shaped clusters of chips for any specific job you're running. And if a chip fails, which happens, the network just routes around it. It contains what they call the blast radius, keeping it small so the rest of the system just keeps on humming. It all adds up to unbelievably efficient, high-speed data sharing with almost no overhead. So what's the bottom line here? It's a new world record for shared memory systems. Simple as that. This kind of architecture unlocks totally new ways to parallelize AI models, making it fundamentally more efficient to train and run the enormous models that are defining the future of AI. So connecting all these chips with light solves the data traffic jam. Fantastic. But now you have a very physical problem. How do you pack all of them so close together without them, melting? That is a completely different kind of engineering beast. The whole physical system is built in layers, kind of like a Russian nesting doll. On the outside, you've got the rack, which handles all the power and networking. Inside that, you find these trays, and each tray holds 4 liquid-cooled Ironwood chips. And then right at the very heart of it all, you have the chip itself, the tiny engine doing all the work and generating all that heat. To handle all that heat, Ironwood uses Google's 3rd-generation liquid cooling. And this isn't just a simple pump. It has something called variable flow control. You can think of it like a super smart thermostat for the supercomputer, constantly adjusting the cooling in real time to be as efficient as possible. But as impressive as the cooling and the networking are, the real magic, the source of that 42.5 exaflops of power, is happening on the silicon inside these trays. So it's time we take a closer look at the chip itself. Okay, let's zoom all the way in and look at the anatomy of the Ironwood chip, because this is where the generational leap in performance really becomes crystal clear. And it is a massive leap. Compared to its predecessor, the TPU V5P, Ironwood delivers over 10 times the raw compute. A huge reason for that is a fundamental shift in architecture. This is Google's first ever dual compute die TPU. They've effectively packed the power of 2 processors into a single, highly integrated package. Inside this dual die package, you've got several specialized engines all working in perfect concert. You have the Tensor Core, which does most of the heavy lifting. Then there's the SparseCore for handling more specialized data. Feeding both of them is ultra-fast HBM3E memory.
And of course, the high-speed interconnect links the chip to the other 9,215 members of the team. So the Tensor Core, that's your primary workhorse. Its job is to perform all the dense matrix and vector math that forms the backbone of pretty much all modern AI model training. This is where the raw teraflops are born. Working right alongside it is the 4th-gen SparseCore. This thing is 2.4 times more powerful than the last one, and it's a specialist. It offloads specific tasks, like handling embeddings, which is just how AI models represent complex concepts as numbers. This lets it run in parallel, freeing up the Tensor Core to focus on what it does best. Of course, all that compute power is totally useless if you can't feed it data fast enough. You can't let the engine starve. That's why Ironwood has 8 stacks of the latest HBM3E memory, and it delivers a staggering 7.3 terabytes per second of bandwidth. It's a fire hose of data that makes sure those compute engines never have to wait. We've talked a lot about raw performance, but at this kind of scale, you start running into the hard limits of physics, and another metric becomes just as critical as speed, if not more so, power efficiency. And this is another area where Ironwood makes a massive leap. It delivers double the performance for every single watt of power it consumes compared to the previous generation. Just think about that for a second. A profound gain of efficiency. You know, the source document for this whole explainer frames the problem pretty bluntly with this one question: who wants nuclear reactors? And that really is the point. You can't just keep throwing more and more power at AI forever. The only sustainable path forward is to become radically more efficient. To achieve this, Google developed a full-stack system called Project Smoothie. It intelligently manages power consumption from the individual chip all the way up to the data center, smoothing out those massive energy spikes you get when you're training large models. It's like a sophisticated shock absorber for the power grid. And the real-world impact of all this efficiency is incredible. The system is designed to achieve 30% more throughput. That's 30% more actual AI work within the exact same power budget of a data center. That's a direct dividend you get from Ironwood's incredibly efficient design. So Ironwood really does represent a new frontier in scale, in performance, and in efficiency. Which leaves us with the ultimate question. With this unprecedented level of AI compute, fused together by light and managed with incredible intelligence, what breakthroughs are now finally within our reach?